Swayam Prabha. Digital India. Educated India.
Welcome to lecture 19 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Testing Structural Break, Parameter Constancy and Model Stability. Now, one of the basic assumption of multiple linear regression model is that the parameters remain constant throughout the sample period. In particular, the regression coefficient vector beta remains constant throughout the sample period. Now, in many applications, this assumption is not satisfied, and if this assumption is not satisfied, your OLS estimator may not remain valid or efficient. Further, your predictions will not be valid in such situations if the parameter is not constant throughout the sample period. Now, such kind of variation in parameter or such kind of changes in the model one may observe say maybe because of some economic crisis or because of some economic reforms, maybe because of some war, etc. For instance, if you look at different econometric models, modeling the different factors of Indian economy, then you will observe that say after 1991 means after the economic reforms which were implemented in 1991, there is a structural change or there is a change in the pattern of different econometric models. For example, if you want to model the currency held by people using GDP, inflation rate, etc., then you will observe that there is a change in pattern of the model after 1991. So, it is important to test whether such a change has really occurred at a particular time point or not. So, in this lecture we are going to consider or discuss different testing procedures for testing such kind of structural changes in the model. So, one of the basic assumption of the linear models is the relationship between dependent and independent variables remains the same throughout the sample period. There is no change in the relationships during the sample period, and this obviously implies the regression parameters remain constant over the entire sample period. We denote the regression parameter by beta, and you take the model y equal to x beta plus u, and this regression parameter vector beta does not change with the sample. So, this remains constant throughout the sample period. Then a change in the structure of pattern of data may be characterized by the change in the regression parameters. So, if there is any particular change in the pattern of the data, it may be reflected in your regression parameters vector, and such kind of changes are called structural changes. So, it is important to check or to test such kind of structural changes, if such changes are present in the model. Parameter instability in models is a common empirical problem in macroeconomics and finance. Often we observe that during the sample period, the parameter does not remain constant, it changes. It may have one change at a particular point of time, or it may have more than one changes. Then some of the examples of structural changes are the oil price shocks or labor productivity changes, stock return prediction models, etc. So, for example, the relationship between inflation and oil prices of US has changed direction and deteriorated in the sense that regression coefficient decreased after the Gulf War oil crisis in 1990. So, if you model the inflation and oil prices of US, then you will observe that there is a change in pattern of the model before and after the Gulf War oil crisis, which occurred in 1990. So, there is a structural change in the model. Then while modeling the consumer pattern data, one may observe shift in the model before and after the war as the economy of the country gets disturbed. So, suppose there is a war in some country, then definitely you will observe a change in the consumer pattern data, or you may observe such kind of changes in consumer pattern if there are some economic reforms implemented in that country during a certain period. You may observe such kind of changes in the model if there is some change in the foreign trade policy of a country. So, there might be different reasons for such kind of changes in the model, but in several applications such kind of structural breaks occur. Then failing to account for structural changes results in the model misspecification, which in turn leads to poor forecasts. So, if you do not take into account such kind of structural changes in the model, then obviously, if you fit the model without taking care of these structural changes and then we use this model for the forecasting purpose, it will lead to poor forecast, because you have not taken into account the structural change. So, now we consider the different tests for specification error. So, analysis of structural change. So, structural change occurs when parameter in a relationship differ from one subset of data to another. So, we assume that there is just one structural change present in the data at observation n 1 plus 1. In all, you have n observations and you have observed one structural change, or you suspect one structural change at time point or at observation n 1 plus 1. So far we have considered just one structural change here, but there might be more than one structural changes also. Then we are considering the structural change at a known time point or at a known observation, or you can say abrupt structural break at a known observation, say n 1 plus 1. But such kind of structural change may occur gradually over a period of time. So, it may occur gradually between n 1 plus 1 to n 1 plus r. Anyway, here we are going to consider this case only when you have just one structural break, the break point is known and the break point is n 1 plus 1. So, now we divide the observations n observations into two parts. So, n 1 observations and n 2 observations. So, that n is equal to n 1 plus n 2. Then we consider the model y equal to alpha ln plus x beta plus u. So, this is the term corresponding to the intercept term, and then x is of order n cross k minus 1. Then we partition y ln and x and u as y equal to y 1 y 2, y 1 is of order n 1 cross 1, y 2 is of order n 2 cross 1. Similarly, we partition ln equal to ln 1 ln 2, x equal to x 1 x 2, x 1 is of order n 1 cross k, x 2 is of order n 2 cross k, and we partition u as u 1 u 2. Then the two subgroup models with no structural change are y 1 equal to alpha L n 1 plus x 1 beta plus u 1 and y 2 equal to alpha L n 2 plus x 2 beta plus u 2. So, here in 1 we are assuming that there is no change in parameters for the two sample periods. Then we consider the case when structural change is due to shift in intercept term only. So, for first n 1 observations, your intercept term is alpha 1, and for the next n 2 observations, the intercept term is alpha 2. So, you can write the model as y 1 equal to alpha 1 L n 1 plus x 1 beta plus u 1, y 2 equal to alpha 2 L n 2 plus x 2 beta plus u 2. Then we combine the two equations and we have the combined vector y 1 y 2 equal to L n 1 0 x 1, then 0 L n 2 x 2, then we have the coefficients vector alpha 1 alpha 2 beta plus u 1 u 2, and you can easily obtain the equation 2 from 2 dash. Say y 1 is equal to L n 1 alpha 1 plus 0 into alpha 2 plus x 1 beta, and y 2 is equal to 0 into alpha 1 plus L n 2 into alpha 2 plus x 2 beta, of course, plus u 2 also. In the first equation also we have plus u 1. So, a structural change is due to shift in both intercept term and slope coefficient. In that case, we write the model as y 1 equal to alpha 1 L n 1 plus x 1 beta 1 plus u 1 and y 2 equal to alpha 2 L n 2 plus x 2 beta 2 plus u 2. Again we combine these two equations and write the model as y 1 y 2 equal to L n 1 0 x 1 0 0 L n 2 0 x 2, and then we have alpha 1 alpha 2 beta 1 beta 2 plus u 1 u 2. So, you can easily observe that in 3 dash, if we simplify 3 dash, then we get y 1 equal to L n 1 alpha 1 plus 0 into alpha 2 plus x 1 beta 1 plus 0 beta 2 plus u 1. So, you get this first equation. Similarly, you obtain the second equation also from 3 dash. Now, we consider the test for structural change. So, when there is no structural change or when the structural change occurs just because of change in intercept term or when the structural change occurs because of change in just slope coefficients, that is betas. So, we apply OLS to models 1, 2 and 3, and then we obtain the residual sum of squares. Say R S S 1 is the residual sum of squares for the model 1, model without any structural change in intercept term or slope coefficients. Then R S S 2 is the residual sum of squares which you have obtained by applying OLS to model 2, that is the model with structural change in intercept term, but no structural change in slope coefficients, and R S S 3 which is the residual sum of squares for model 3, that is the model which incorporates both the structural change in intercept term as well as the structural change in slope coefficients. Now, the corresponding degrees of freedoms are with R S S 1 you have n minus k degrees of freedoms. Well, you have just k explanatory variables, 1 intercept term and then k minus 1 axis. So, the degree of freedom of R S S 1 is n minus k. Then for R S S 2, the degree of freedom is n minus k minus 1. Actually, in the second model, you have k plus 1 explanatory variables. So, if you consider this model 2, then you have 1 explanatory variable here, 1 here and k minus 1. So, in all you have k plus 1 explanatory variables in model 2. So, the degree of freedom is n minus k minus 1. Then corresponding to model 3, the degree of freedom of residual sum of squares is n minus 2 k. Actually, in the third model, you have total 2 k explanatory variables, 1 plus k minus 1 plus k minus 1. So, the degree of freedom is n minus 2 k, and we assume that n 1 is greater than k and n 2 is greater than k. Of course, you require this assumption, otherwise you will not be able to apply OLS to two equations. Now, suppose you want to test the hypothesis alpha 1 equal to alpha 2. Your alternative is H 1 not H naught. And here we also assume that there is no structural change in betas. So, you already assume that beta 1 is equal to beta 2. So, the F ratio is quite simple. You take R S S 1, the residual sum of square for model 1, which is the model under H naught, minus R S S 2, which is the residual sum of square corresponding to the model 2, that is corresponding to the model under the alternative hypothesis H 1, and then we divide it by the corresponding degrees of freedoms. Notice that the degree of freedom of RSS 1 is n minus k, and degree of freedom of RSS 2 is n minus k minus 1. So, the degree of freedom of RSS 1 minus RSS 2 is actually 1, and then we divide it by RSS 2 divided by the corresponding degree of freedom, and under H naught this follows F distribution with 1 and n minus k minus 1 degrees of freedoms. So, now you can easily form the critical region. If this calculated value of F is tabulated value of F at say alpha level of significance and 1 and n minus k minus 1 degrees of freedoms, then we reject H naught at alpha level of significance. In fact, if you take a square root of this F statistic, because you have 1 degree of freedom here, then it reduces to the t test, and it is quite obvious also you can apply t test for testing alpha 1 equal to alpha 2. You have to test the equality of just a single coefficient alpha 1 equal to alpha 2. So, you can apply the t test. Now, next we consider H naught beta 1 equal to beta 2. So, we assume that the structural break is because of change in slope coefficients. Alphas do not change. Then we consider RSS 2 minus RSS 3. Now, the degree of freedom of RSS 2 is n minus k minus 1, and RSS 3 is n minus 2 k. So, their difference is k minus 1. So, we divide it by k minus 1, and then we divide it by RSS 3 divided by n minus 2 k. And under H naught this follows a F distribution with k minus 1 and n minus 2 k degrees of freedoms. So, again you can easily form the critical region for testing H naught. The third case which we consider here is H naught is the hypothesis that alpha 1 is equal to alpha 2, beta 1 equal to beta 2. So, under H naught we assume that there is no structural change, and under H 1 we assume that there is a structural change in both interceptor and the slope coefficients. So, basically we are testing model 1 against 3. So, here actually we are testing model 1 against 3. Here we are testing model 1 against 2, whereas in this case we are testing model 2 against 3. So, again the F ratio is RSS 1 minus RSS 3 divided by k upon RSS 3 divided by n minus 2 k, and under H naught this follows F distribution with k and n minus 2 k degrees of freedoms. So, again you can easily form the critical region using this result. Now, we consider this general case. So, we assume that there is just one structural change in all the parameters, and the structural change has occurred at n 1 plus 1th observation. Again we divide the observations into two parts, first n 1 and next n 2. So, that n is equal to n 1 plus n 2. Here y 1 is of order n 1 cross 1, x 1 is of order n 1 cross k, u 1 n 1 cross 1, y 2 is of order n 2 cross 1, x 2 n 2 cross k, and u 2 is of order n 2 cross 1. Now, combining the two equations, we can write the model in this form: y 1 y 2 equal to x 1 0 0 x 2 beta 1 beta 2 plus u 1 u 2. Then you can easily verify that if you take the transpose of this matrix and multiply it by this matrix, then you obtain the matrix x 1 transpose x 1 0 0 x 2 transpose x 2. And if you take inverse of this matrix x 1 transpose x 1 0 0 x 2 transpose x 2 whole inverse is equal to x 1 transpose x 1 inverse 0 0 x 2 transpose x 2 inverse. Now, the null hypothesis of no structural changes at naught beta 1 equal to beta 2, or equivalently beta 1 minus beta 2 equal to 0. Now, if you take r equal to I k minus I k small r equal to 0, then you get the hypothesis r beta 1 beta 2 equal to beta 1 minus beta 2 and then equal to 0, because small r is equal to 0. OLS estimator of beta 1 beta 2 is b 1 b 2 equal to x 1 transpose x 1 inverse, x 1 transpose y 1, x 2 transpose x 2 inverse, x 2 transpose y 2. You can easily verify it. You have to multiply this by y 1 y 2. So, you multiply this by y 1 y 2 and then you get this expression for the OLS estimator of beta 1 beta 2. Further, r b 1 b 2 minus small r is equal to b 1 minus b 2. And if you consider this matrix r x transpose x inverse r transpose, since r is equal to I k minus I k, you get x 1 transpose x 1 inverse plus x 2 transpose x 2 inverse here. And then the F test statistic is F equal to b 1 minus b 2 transpose, then in between you take inverse of the matrix x 1 transpose x 1 inverse plus x 2 transpose x 2 inverse, and then you have b 1 minus b 2 divided by the corresponding degree of freedom, which is k upon E transpose E upon n minus 2 k. And under the null hypothesis, this follows F distribution with k n minus 2 k degrees of freedoms. And then you can easily form the critical region for testing H naught. Now, we consider an alternative derivation of the F test. Now, suppose E star is the OLS residual under restricted regression, that is when beta 1 is equal to beta 2, and E is the OLS residual under unrestricted regression. So, E transpose E is equal to y 1 transpose y 1 plus y 2 transpose y 2 minus b 1 transpose x 1 transpose x 1 b 1 minus b 2 transpose x 2 transpose x 2 b 2. In fact, to obtain E, you simply take y equal E equal to y 1 y 2 minus x 1 0 0 x 2, and then you have b 1 b 2 here, and then you can easily obtain E transpose E. then E star transpose E star is equal to y 1 transpose y 1 plus y 2 transpose y 2 minus B 1 transpose x 1 transpose x 1 plus B 2 transpose x 2 transpose x 2. In between you have x 1 transpose x 1 plus x 2 transpose x 2 inverse, x 1 transpose x 1 B 1 plus x 2 transpose x 2 B 2. To derive E star, we have y 1 y 2 here minus, now your matrix of explanatory variables is x 1 x 2, when beta 1 is equal to beta 2, you take this matrix and then you obtain the OLS estimator B here. So, this is how you can get E star. Just write the expression for B here and then you get E star, and then you can obtain E star transpose E star. And then you can write E star transpose E star as y 1 transpose y 1 plus y 2 transpose y 2 minus B 1 transpose x 1 transpose x 1. Then in between you have x 1 transpose x 1 plus x 2 transpose x 2 inverse, x 1 transpose x 1 B 1. Then you get this term minus B 2 transpose and so on B 2, and then you also have the cross product term, means you multiply this by this matrix and then this term, then you multiply this by this matrix and this term, you get the cross product term, again you multiply this by this matrix and the first term, and then you multiply this term with this matrix and this term. So, you obtain this expression. Then we make use of this, the result that x 1 transpose x 1 into x 1 transpose x 1 plus x 2 transpose x 2 inverse x 1 transpose x 1. This is equal to x 1 transpose x 1 plus x 2 transpose x 2 minus x 2 transpose x 2, and then you have inverse of this matrix into x 1 transpose x 1. And then you get identity matrix here, x 1 transpose x 1 plus x 2 transpose x 2 into inverse of this matrix. So, you obtain x 1 transpose x 1 minus x 2 transpose x 2, x 1 transpose x 1 plus x 2 transpose x 2, and then inverse of this, and then you have x 1 transpose x 1, and then you get x 1 transpose x 1 minus, now you take this matrix inside the inverse and then this matrix also inside the inverse. So, finally, you obtain this matrix x 1 transpose x 1 minus x 1 transpose x 1 inverse plus x 2 transpose x 2 inverse whole inverse. And then you get y 1 transpose y 1 plus y 2 transpose y 2 minus B 1 transpose x 1 transpose x 1 B 1 minus B 2 transpose x 2 transpose x 2 B 2. And then similarly, you simplify this expression also, and this expression you simply take x 1 transpose x 1 inside and x 2 transpose x 2 inside. So, you get this matrix here, and then you combine all the three terms, this term and this term. So, you get B 1 minus B 2 transpose x 1 transpose x 1 inverse plus x 2 transpose x 2 inverse. Then you have B 1 minus B 2, you have whole inverse also, and under H naught when beta 1 is equal to beta 2. Now, we define the F ratio equal to E star transpose E star minus E transpose E divided by K upon E transpose E divided by n minus 2 k, and this follows F k n minus 2 k. So, here I have given the detailed derivation of F ratio also. So, for the model beta 1 equal to beta 2, we write the model as y 1 y 2 equal to x 1 x 2 beta plus u, and then the OLS residual is E star equal to y 1 y 2 minus x 1 x 2, and then we apply OLS to this model. We get x 1 transpose x 1 plus x 2 transpose x 2 whole inverse x 1 transpose y 1 plus x 2 transpose y 2, and then E we have already obtained E is equal to y 1 minus x 1 transpose x 1 inverse x 1 transpose y 1 y 2 minus x 2 transpose x 2 inverse x 2 transpose y 2, and then E transpose E is equal to y 1 transpose y 1 plus y 2 transpose y 2 minus b 1 transpose x 1 transpose x 1 b 1 minus b 2 transpose x 2 transpose x 2 b 2. So, the calculation of E transpose E is straightforward. Now, we calculate E star transpose E star. So, using this expression for E star, we obtain E star transpose E star as y 1 transpose y 1 plus y 2 transpose y 2 minus b 1 transpose x 1 transpose x 1 plus b 2 transpose x 2 transpose x 2. In between we have this matrix, and then we have this expression x 1 transpose x 1 b 1 plus x 2 transpose x 2 b 2, and then we simplify it. So, we get the first two terms, and then b 1 transpose x 1 transpose x 1, then we have this matrix here, and then we take x 1 transpose x 1 b 1 here. Then minus we take b 2 transpose x 2 transpose x 2, then we have this matrix x 1 transpose x 1 plus x 2 transpose x 2 whole inverse x 2 transpose x 2 b 2, and minus 2 times we get the cross product term b 1 transpose x 1 transpose x 1, then x 1 transpose x 1 plus x 2 transpose x 2 inverse x 2 transpose x 2 b 2, and then we simplify it. For that purpose, we observe that x 1 transpose x 1 minus x 1 transpose x 1 plus x 2 transpose x 2 inverse x 1 transpose x 1 is equal to, we simply write x 1 transpose x 1 equal to x 1 transpose x 1 plus x 2 transpose x 2 minus x 2 transpose x 2, and then we have derived this expression, and finally, you obtain x 1 transpose x 1 inverse plus x 2 transpose x 2 inverse whole inverse. Similarly, you can simplify this second expression also. Further, x 1 transpose x 1 plus x 1 transpose x 1 plus x 2 transpose x 2 inverse x 2 transpose x 2 is equal to this, because you take x 1 transpose x 1 inside the inverse from this side and x 2 transpose x 2 inside the inverse from this side. So, finally, you obtain this expression. So, you get this quantity, which is equal to b 1 minus b 2 transpose x 1 transpose x 1 inverse plus x 2 transpose x 2 inverse whole inverse b 1 minus b 2. Then we substitute this expression in equation 2 and you get 1. Now, we consider Chow forecast test for testing the model stability. So, we consider the linear model y I equal to x I transpose beta plus u I equal to 1 to n. Then in equation 1, we assume that the regression coefficients vector beta is constant. Then we divide the sample into two parts of sizes n 1 and n 2. So, that n is equal to n 1 plus n 2. Then y I is equal to x I transpose beta 1 plus u I for I equal to 1 to n 1, and then we write y j equal to x j transpose beta 2 plus u j for j equal to n 1 plus 1, n 1 plus 2, so on n 1 plus n 2, which is equal to n. Or you write y 1 equal to x 1 beta 1 plus u 1, y 2 equal to x 2 beta 2 plus u 2, where y 1 is of order n 1 cross 1, x 1 n 1 cross k, u 1 n 1 cross 1. Similarly, y 2, x 2 and u 2 are of orders n 2 cross 1, n 2 cross k and n 2 cross 1 respectively. Now, we want to test the hypothesis beta 1 equal to beta 2 against the alternative not H naught. Then these are the steps for the Chow forecast test. We estimate beta by applying OLS to first n 1 observations. So, you get B 1 equal to x 1 transpose x 1 inverse x 1 transpose y 1. So, this is the OLS estimator of beta based on first n 1 observations. Then we use this OLS estimator to predict y 2. So, y 2 head is equal to x 2 b 1. So, this is the predicted value of y 2 based on first n 1 observations. Then prediction error is d equal to y 2 minus y 2 head or y 2 minus x 2 b 1. This is the prediction error. Now, under H naught beta 1 is equal to beta 2 equal to beta say. So, if y equal to x beta plus u and expectation of u transpose is equal to sigma square u I n holds for both data sets, then d is equal to x 2 beta plus u 2, y 2 is equal to x 2 beta plus u 2 minus y 2 head, which is equal to x 2 b 1. So, you can write it as u 2 minus x 2 b 1 minus beta. Then expectation of d is equal to expectation of u is 0, and if beta 1 is equal to beta 2 equal to beta, then expectation of b 1 is equal to beta. So, expectation of the second term is also 0. So, under H naught expectation of d is equal to 0. Then we obtain the variance covariance matrix of d, which is expectation of d transpose. So, expectation of d transpose is equal to, say, first you get expectation of u 2 transpose, which is equal to sigma square u I and 2. Then you have a term x 2 b 1 minus beta b 1 minus beta transpose x 2 transpose, and then you take expectation of this. So, you get x 2 sigma square u x 1 transpose x 1 inverse, then x 2 transpose. The variance covariance matrix of B 1 is sigma square u x 1 transpose x 1 inverse. And then you also have a cross product term like this, say x 2 b 1 minus beta u 2 transpose. Now, this has expectation 0, because b 1 minus beta is actually equal to x 2 x 1 transpose x 1 inverse x 1 transpose u 1, and then you have u 2 transpose. Expectation of u 1 u 2 transpose is equal to 0. So, the cross product terms have expectation 0. So, you get this expression for the variance covariance matrix of D, and we denote it by V D say. Then if U follows a normal distribution with mean 0 variance covariance matrix sigma square u I n, then under H naught D follows normal distribution with mean vector 0 and variance covariance matrix V D. So, under H naught D transpose V D inverse D follows a chi-square distribution with n 2 degrees of freedoms, and E 1 transpose E 1 upon sigma square u, this follows a chi-square distribution with n 1 minus k degrees of freedoms independently of D. E 1 is the OLS residual for which is based on B 1. So, E 1 is equal to y 1 minus x 1 B 1. So, under the null hypothesis H naught of parameter constancy, if we take the ratio D transpose I n plus x 2 x 1 transpose x 1 inverse x 2 transpose whole inverse D divided by the corresponding degree of freedom n 2 upon E 1 transpose E 1 divided by n 1 minus k, the corresponding degree of freedom. Then this follows F distribution F n 2 n minus n 1 minus k under H naught. Then there is an alternative derivation of Chow forecast test, which I am going to give you here. Say, suppose you write gamma equal to x 2 alpha minus beta, and suppose we can write the complete model as y 1 equal to x 1 beta plus u 1 and y 2 equal to x 2 alpha plus u 2. Here actually I have slightly changed the notation. Instead of beta 1 I have taken beta here, and instead of beta 2 I have taken alpha here. So, then you can write this alpha as say x 2 alpha is equal to x 2 beta plus gamma plus u 2. Now, if gamma is equal to 0, we have alpha equal to beta. So, our hypothesis of parameter constancy actually reduces to the hypothesis gamma equal to 0. So, now you have to develop test for testing the hypothesis gamma equal to 0. Then we can write the model in the form y 1 y 2 equal to x 1 0 x 2 I n 2 beta gamma plus u 1 u 2. Now, suppose we write z equal to x 1 0 x 2 I n 2, then z transpose z is equal to x 1 transpose x 1 plus x 2 transpose x 2. Actually, z transpose is equal to x 1 transpose x 2 transpose 0 I n 2, and then you can easily obtain z transpose z, and then you have x 2 transpose here, x 2 here and I n 2. So, inverse of z transpose z we write equal to say C D E F. Now, what you have to do? You take z transpose z inverse z transpose z equal to I k, or you can say you multiply this z transpose z by C D E F, and you multiply this C D E F by z transpose z, and then you write this equal to I 0 0 I, and then you equate the corresponding terms. So, you obtain C equal to x 1 transpose x 1 inverse, D equal to E transpose equal to minus x 1 transpose x 1 inverse x 2 transpose, and F is equal to I n 2 plus x 2 x 1 transpose x 1 inverse x 2 transpose. Then the OLS estimator of beta gamma is B c equal to, you can apply OLS to this equation and then you can easily obtain x 1 transpose x 1 inverse x 1 transpose y 1 and C is equal to y 2 minus x 2 x 1 transpose x 1 inverse x 1 transpose y 1. Now, notice that this C is equal to D. Here you get B 1 and this C is equal to D. So, estimate of gamma which is C is simply the prediction error D equal to y 2 minus y 2 head or y 2 minus x 2 B 1. This is your B 1. So, you can write the model as y 1 y 2 equal to x 1 x 2 0 I and 2 plus k B 1 D plus E 1 E 2. E 1 E 2 is the OLS residual and E 2 is equal to y 2 minus x 2 B 1 minus D which is equal to 0. So, the OLS residual sum of square E transpose E is equal to E 1 transpose E 1 and then you test this hypothesis gamma equal to 0. So, your test statistic is F equal to D transpose, then in between you have the variance covariance matrix whole inverse T divided by N 2 upon E 1 transpose E 1 divided by N 1 minus k, which follows F distribution. So, you get the same statistic. Then the main problem with the Chow test is the choice of N 1. Then there are some alternative test procedures also, which I am not going to discuss here, and those test procedures are given by Hansen or Brown, Durbin and Evans. In fact, to derive this test statistic, you have to test this kind of linear hypothesis. So, you take you have this test statistic. So, you take z equal to this matrix, you replace x by z, you take beta equal to beta gamma, r equal to 0 I n 2, n equal to n 1, q equal to n 2 and then you get this test statistic. So, in this lecture we have considered different tests for testing the specification error, like for testing the structural change or parameter consistency of the multiple linear regression model. We have discussed several examples where we observe such kind of structural changes. If we ignore such kind of structural changes at the estimation stage, then it may lead to poor estimators. Not only that, it also leads to poor forecasts. Although in this lecture I have considered the case of a single structural change and then we have also assumed that the change point is known, but one may consider the case of multiple structural changes. Often we observe more than one structural changes. Then sometimes certain period in which the change might have occurred, but you do not know the exact point of the change. So, there are inference procedures like estimation and testing procedures, which have been developed encounter such kind of problems. Then we have only considered the case when there is an abrupt change, means there is a sudden change at a particular observation or at a particular time point, but one may consider the case when there is a gradual change over a certain time period. So, here I am going to stop. Thank you.
Hello, good morning everybody. I am Raghunandan Sengupta. So, I will just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance as I mentioned. Now, we all know that in 1997 the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development. So, obviously due to some regulation errors or something, there has been some pitfalls, which I think is should be a bullet point for people who are really interested to take up quantitative finance, they should be aware. So, consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So, what should be done? So, the main thing is that even if you know the technique is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner, such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall the in-depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.